Okay, hey, thanks everyone for coming, for showing up in person. I'm pretty excited. I gave the bulk of this presentation actually when I first started at City Light, so about a decade ago. So if you were here for that meeting, this may ring a bell, but there's a lot of new faces out there. So we've been studying stream-type juvenile Chinook habitat use in the basin for a very long time. The research started as a result of the Chinook Recovery Plan, which is the reason why I think everybody's here today. And within that Chinook Recovery Plan, the stream-type juvenile, and those are, just back up really quick, those are the juvenile salmon that reside in the river for a year before they out-migrate. And I'll go through different life histories in the next slide or two. But the stream-type juvenile was identified as a pretty important component of the Chinook population, and there was not a lot known about that. And I'll get into a little more detail on that in the next slide. So within salmon populations, life history diversity is pretty important. So if you look at this like blue, yellow, pink figure right here, you'll see that at the top, emergent fry, they come out of the gravel. And if you follow the left side of this figure, you'll see they migrate downstream as fry, and then they can kind of they have two little options. So they can migrate straight through on out to Whidbey Basin as a fry migrant. They can migrate through and rear in the nearshore environment as a nearshore fry migrant or nearshore rearing migrant. Or on the right side, you can see they could go down and rear in the Natal Estuary, the Skagit Estuary, and then eventually move on out to the ocean. And that's why this part in particular is why a lot of restoration efforts have been focused on the estuary. But then if you look on the right-hand side of the figure here, there's a couple more options. They'll rear in fresh water after emerging as a fry. First option would be to rear for several months and then migrate through. These are what we call par migrants. Some people call them 90-day wonders. And then on the right-hand side, you can rear for a year and then migrate on through, and that would be the yearling migrant. So there's a variety of freshwater, there's a couple of freshwater rearing life histories, and there's a lot more detail in the recovery plan. So if you want to get a good review, go through the recovery plan and explains it all. Now, why is this important? Well, it's important because life history diversity allows for the population to be more robust to environmental effects. So here in the Northwest, we have a bunch of volcanoes. Those can have a short-term large effect on fish habitat and their populations, or you can see here's a canyon on the right-hand side. Slow geologic processes can also have an effect on these fish. And if you look at this figure on the lower right, you can see here's the fry migrants and the delta and the par migrants and the yearlings. And you can see that each color in that bar represents one of the 6 Chinook stocks we have here in the Skagit River. And you can see that within each of these populations or stocks, they have a different contributions of all these different life history types, but they're all there. They're all present within each one of these populations. And so understanding what makes all that work, or a little bit of what makes all that work, is pretty important when we're managing and restoring these ecosystems. So another big effect is hydrology. Hydrology can have a large effect on these juveniles as they're rearing in fresh water, or maybe selecting not to rear in fresh water and leave the river system. And so just for a variety of reasons, having that a diverse portfolio of life histories is important for the resilience of the populations. So here's just a good example of one reason why having a diverse life history is important. On the right-hand side, you'll see like your typical yearling Chinook migrant. On the left-hand side, your typical par migrant. And Chinook yearlings have larger size of out-migration, so do par compared to fry. But the small to adult survival for the yearling migrant is twice that of the par migrant. And I don't have the numbers in front of me or with me, but and of course both of these have a higher adult to or small to adult survival than a fry migrant. So it's all very important for keeping that diversity within the population. And of course there's cultural importance. There's tribal culture that values salmon, local culture also at the bottom. also values the salmon. I mean, when I was a kid growing up in Ballard, salmon was always on our table because it was cheap and it was good for you, and was a very important part of my upbringing and for many other people's upbringing. So for Chinook recovery planning, it's important to consider various aspects of the life histories and performance of these populations. And so, first of all, as recovery planning was underway, a decline in stream-type life histories was identified, and also declines in spring Chinook spawners was also identified. So initially, back in the early 2000s, a lot of people associated these like prolonged rearing smolts, these yearling types or stream types, if you will, were associated with spring Chinook, which is true. But as you saw on the previous slide, they also contribute to other stocks within the basin. So in general, it's an important consideration with regards to recovery and population productivity. The recovery plan specifically, though, identified a data gap in yearling distribution and habitat use. So I want to make sure that's clear. We didn't know where they were, and we didn't know what their habitat was. We're supposed to be recovering species, yet we were uncertain as to really what is juvenile Chinook habitat. And so the take-home message, though, is that if we can work towards addressing some of these limiting factors that are responsible for the decline in these populations, we should see an increase in productivity within the population as a result of higher survival rates and a variety of other important factors. The first question that we had was, can we find them? If we're going to look for these juvenile Chinook in the river system, we need to be able to locate them, because if you can't find them, you don't know what habitat they're using, and you can't really effectively work towards recoveries. So this is we'll cut to the chase. This was the report that was written as part of phase one. And so phase one looked at sort of the basics of what we know about this life history and the adults that usually are, what's the right word, a beneficiary of having that life history. So on the right-hand side, you see in the white, those are the spring populations in the Skagit. On the left, those are the summer fall in that kind of salmon color. There's a bunch of mixed stock river reaches that you're probably familiar with from like the Watershed Council strategic plan and things like that. And, tier 1, tier 2, tier 3 for all of you on the twig. The spatial strata initially in this first phase, we looked at the juvenile rearing ranges for all the 6 different stocks of Chinook in the basin, which included regulated, unregulated hydrographs, and then also basin hydrology. So we have rain and snow and rain on snow or rain snow mixed hydrographs within the system. And so the initial thought was those are going to be important factors driving this life history. What we ended up doing was a large scale pilot study. So really we had a couple major questions: was where are the rearing habitats for these fish, and what's the quantity of the habitat by type. So initially it was a couple sampling seasons, late summer, late winter. Those are important periods for where you might see limitations on growth or habitat or both, and survival, I should say, those 3 factors. And then, so 7 sites were selected. It was, fish were observed via snorkeling. And then there was a comparison of day and night, because oftentimes these juveniles are nocturnal. They'll hide during the day, and so you can only observe them at night unless the stream temperature, water temperature is of a certain point, and then they'll be out. So anyway, we wanted to test that assumption as part of this work. Also, what came out of this is this figure on the right there, which is essentially hand delineated habitat features through the whole main stem Skagit River. So that's an excellent data set that SRSC put together, and it's still a valuable tool today, where you have like, where are the log jams, where are the bars, where are the banks, where are all these backwaters and all these other features in the river system. So that was a great outcome of this study. This is just a reminder of where all these different stocks are located. So we have our 3 spring populations in the Cascades, Sewaddle, and the upper Sauk, and then the green and blue, those are our summer populations, and the red is the fall. We knew that yearlings would be present in all these populations, and so that was also a consideration in this work. And so I'm not going to go through all these figures, but just to show that fish were found, juvenile Chinook were found in most of these locations. Maybe not every season, but they were present, and they were present in different abundances. So we knew that we could find them. That was good. That was the main goal of this phase of the study. And out of the study came a few recommendations for future work. One was that you have to look in the areas other than just the main stem. You have to look at all the different habitats that were present associated with at least main stem, or if a better option would be anywhere Chinook are spawning. Randomize the site selection, just do night snorkeling the whole time. And then the effort, we did a power analysis and found that the effort needed to be tripled in the summer and at least doubled for winter. And then adding a third sampling period was also recommended. So that's what we did. We put all that together for phase 2. And the main question there was, where do we find them? And so this is called the yearling study, or phase 2, if you will. And we went out and applied all that we learned from the first phase and the recommendations into the second phase. So we're going to go through the objectives here, and then a little bit on how we broke out the river basin to sort of meet all to incorporate all the recommendations and to meet these objectives. And then I'm just going to do a little bit of the results, and that'll kind of bring us to the end of my portion of the talk. But the main objective was to determine the distribution of yearling Chinook. We included steelhead in this one too, so Chinook and steelhead within the Skagit system, and then identified the habitat types that are used by these fish. When you think about habitat type, we kind of split it up into 3 different levels of a hierarchy. We had like a primary, which are these like physiographic units of, like rain, snow, and mix based on hydrology, and the secondary, which is just like main stem, tributary floodplain channel, log jams, things like that, tributary junction as well. And then this tertiary, these are really common in a lot of the stream research, a lot of the literature focused on habitat use. So you have like pool, glide, riffle, bank, bar, backwater, things like that. Those habitat units were considered in phase 1, found to be difficult to differentiate them, like at least with the data we were generating from them. But we recognized that they may be important, and so we included them and we delineated them in the data set that came out of this study. So methods, it was all night snorkeling. We identified species and size structure during the snorkel surveys. We took habitat measurements during the day. I think that's a velocity measurement that's being taken there in the corner. Some drift netting to look at available food, and electrofishing to get our hands on fish to get more accurate size and species composition. And so what we found, some of the results from the study, is that size structure is very similar among hydro regions, but we did see the largest yearlings in sort of the mixed rain and snow hydrographs. Little evidence of bimodality in summer as far as in size. And so what that told us is that, most of the Chinook we find in the summer period are from a single cohort. So they're that year's fish that have established territories, that have elected not to migrate as a par and are likely going to overwinter. And so if you're looking for stream type Chinook in your river system, look at the end of summer, and that's, if they're there, you're likely to find them. But the detection rate was actually really low in the winter. Finding them in the winter was very difficult for the team. And so just bear that in mind when you're looking at these results. I believe Jen's results were different, and which she'll talk about in a second. And so this is one way to analyze a large data set. I'm not going to Analyzing these big data sets requires different analytical tools. In this case, we use this thing called a classification and regression tree. These CART models are kind of like big data analytical tools. They find patterns within the data set that might help you ask more pointed questions and allow you to identify patterns that aren't apparent just by plotting data, for example. And so take-home message here is that we saw some relationship between distance upstream and presence, and we saw some relationship or some differences between the size of the channel and the type of cover that was associated with the fish. Now, these aren't things you should take home and say, this is exactly what we need. if we're building Chinook habitat, but it is a pattern that was identified that warrants future investigation. And so this is another presentation of the data here. This is just a graphical representation of what was observed. Take-home message here was that when you're looking at the results that we saw, at least for Chinook yearlings, is that, in the snow-dominated hydrographs, we saw them in floodplain channels in spring and summer main stems. In the summertime, we saw them in main stems. In the mixed hydrographs, we saw them in spring and summer, kind of in all channel types. And in winter, they're more common in floodplains. So you can kind of see these are just general patterns we identified that might help us ask more focused questions for future investigations. And well, here's Jen with the rest of the story.
Okay, so moving into phase 3, our segment of the study squishes things in on a little bit of a smaller scale. So we kind of, in phase 1, identified these big picture kind of watershed scale preferences, and then Erin talked about habitat type preferences and characteristics, and then we really wanted to know what habitat elements are specifically associated with higher densities, and hopefully some of these elements could be used like in design or as evaluative criteria for specific features. So this paper was published in Transactions in May of 2024. So if you want all the nitty-gritty details, you can go find it. It's the cover story. So we'll show you a picture of that later. But let's move on to the next slide. So another reason we really wanted to do this was to not just learn more about factors contributing to the yearling smolt life history, like Mara suggests from her 2015 article as being necessary, but also to look at some of the tools that are being used to evaluate habitat quality in a variety of places, not just in the Skagit. So this habitat suitability curve for juvenile Chinook, and I believe it was derived from some yearling Chinook observations, is published in the 2022 in-stream flow guidelines from DFW. And people use these curves for the habitat index, habitat suitability, or HSI modeling, and folks have heard about that. And I kind of struggle with this one a little bit because I see these 3, 4, and 5 feet as being ranked as the highest for yearlings, and that's not exactly what we observed when we went out there and looked for them in the Skagit. So that's one of the things that I think, it's neither here nor there, but one of the things that I wanted to find out about, why does this curve say one thing and we're seeing another thing, and maybe that's a follow-up from this. But learning more about yearlings is important. And our focal questions were, which of these elements, including depth, velocity, cover, large wood, specifically temperature, and substrate, are most closely tied to differences in densities for those stream type juveniles. And that's habitat unit agnostic, right? It doesn't matter if it's a pool or a riffle or a slide or a run or whatever you want to call it. These are things that are objective rather than subjective. They can be measured, and they vary with those habitat units, but they don't depend on, what John might call a pool and I might call a pool might be 2 different things. So we wanted to get away from that subjective stuff and utilize relative measurements that are part of design, right? When we make a hydraulic model looking at a plan, we model depth and velocities, and we can look at that map and we can sort of say, does it match up with what we want for Chinook or not? So we wanted to be useful. And then the second part of the study was, as Erin was asking too, do these preferred ranges vary by season, and are the fish responding differently depending on what season? Our study design did leverage some of the data from Erin's work as part of our power analysis. So we ran a power analysis using his data, as he had run using the previous study's data, to see how many sites we needed. So we ended up with 70 locations, 35 in the Skagit and 35 in the Sauk. And the Skagit River sites were mostly in those side channels and floodplain channels that he mentioned, because there weren't a lot of huge log dams. There were a few backwaters that we did sample in the Skagit, and our sites are distributed from the Sauk River on the right-hand side of the upper frame to about River Mile 91, the right-hand side. The left-hand side is the Sauk River, and the right-hand side is River Mile 91. And then for the Sauk sites, those were distributed between River Miles 32, which is about where the White Chuck comes in, because you can't see much downstream of the White Chuck, up to River Mile 40. And that was also identified as an area by WDF&W staff that there had been some spring Chinook spawning. So we were hoping that we'd hit the spring Chinook there, of the yearlings or the stream type juveniles. Thank you. So like Erin's study, we also sampled in multiple seasons. We sampled multiple seasons over multiple years. So we had 2 summers, 2 winters, and 2 springs. And all of our snorkeling was at night, including in the winter in the snow. And that was really fun. We had concurrent daytime habitat measurements. So same day, we would go out and set up the daytime transects, do our measurements in multiple transects for each sample location. And then that same night, go in and do the snorkel surveys. We waited long enough in between the habitat measurements and the snorkeling to not have an effect on fish. So we'd let them rest or, figure out what they were going to do and then come back, usually an hour after sunset to get in the water and do the snorkeling. And we look specifically at depth, velocity, substrate cover, temperature, those types of elements in the field. And then using the field data as well as some remotely sensed information, easting and, distance from the main stem and a few other things, we developed a generalized linear mixed model, which are good if you have non-normal distribution and if you have clumped data, which fish like to do. And we also included a couple of additional factors regarding interaction. So mean depth and mean velocity interaction was included because we thought those would travel together and probably be relevant to fish distribution and density, and then range of depth and range of velocity in terms of how variable the sites were during the, across the site that was sampled. And from that, I know it's sort of a boring table, but these are the results, so we have to walk through them. We developed 3 models, and because of the big flood in November of 2021, our winter 2022 numbers were very, very low because the fish kind of got washed out to some extent. So our winter model is based on that one sample event in winter of 2021 because the numbers were just too small to resolve in 22. But in the summer, the 2 summers that we looked, we found several factors that resolved as significant. Mean velocity, range of depth, maximum water temperature, wood cover, and distance to the main stem. And that's distance, if you're in a side channel, distance from where that sample reach was to where the side channel connects to the main stem Skagit. So how far do those fish, if they didn't spawn in the side channel, how far did they have to travel up the side channel to hang out? And what was kind of interesting was that range of depth was negatively correlated, or the coefficient was negative. And it's kind of counterintuitive, but what we came to sort of believe is that in some of these areas where the water got really thin, they maybe were looking for stability, right? So that if you're coming into areas that have really shallow water and maybe a deep spot, the risk of isolation is higher, and maybe they're moving out of those areas that have, sort of that up and down, and they want something that's stable that they're going to be able to hang out in for a while. I know I'm anthropomorphizing the fish, but this was our interpretation of that selection. And then the max water temperature was also kind of a funny positive correlation. We thought, well, that's interesting with summertime, but when we look at the actual data, those temperatures are not extremely high. The highest densities were around like that 15, 16 degrees. And if we look in the literature, that's sort of the optimum for biomass addition. So they're not outside of the norm in that selection of the upper end of the water temperature in the summer in terms of correlation with high densities. And then the distance to main stem, just noting that is a negative correlation. So there is a limit to how far these fish want to go up into a side channel to rear, at least from our data sets. Winter, slightly different parameters that are driving the winter densities, the range of depth, again, that negative correlation. And, this may be for other reasons in that the shallow water or the very varied, and I'm more focused, I think, on the shallow than I am on the really deep. You may have instances of freezing or things like that may just be less thermally insulating for fish, and they may be picking areas that have some stability in terms of depth. Other factors that were relevant during the winter were the intermediate sediment size, or the D50, right? So your sort of mean sediment size. And that is a positive correlation, but you'll see later in sort of the data summary that we're not talking about huge sediment here. We're talking about relatively small across the board. So the fact that it's positive doesn't really matter. It just means it's somewhat significant depending on, where they are. And of course, wood cover is significant in winter and summer. And we see it's a little bit even more significant in winter than summer based on our curves that we'll see in the later part of the analysis. But definitely important. There's sort of a dearth, it seems like, of papers that associate wood cover with yearling Chinook or stream-type juvenile Chinook. So this is one that does, and if you're looking for that reference, you can find it here. And then distance to main stem, again, that negative correlation, similarly across all seasons. And we'll go into spring real quickly. Just a slight difference in terms of the types of factors that are pushing the densities in spring. That range of depth, range of velocity interaction factor comes into play, range of velocity and range of depth again separately. And, spring's kind of a volatile time. I think we can have some peak flows, we can have some low flows. And again, things that are changing a lot may just be less desirable in terms of fish selection, and it would be interesting to dig into that a little bit more, but that's what the model is saying from this perspective. And then of course substrate played a role, and the distance to main stem was also relevant. We did see, Erin was talking about numbers of fish. We did see a decent number of fish. So the bottom line shows your total STJ Chinook salmon count. So over 1,000 for our 2 summers, and then 600 in that one winter, and a few less, 516 in spring. So these aren't just based on 10 fish, it's based on, quite a few observations. One of the other analytical approaches that we wanted to use was to look at the relative direction and importance by element. So in models that have multiple factors, one of the things you can do is hold all other factors at their mean and vary one factor. And then sort of reverse the model so it's a predictive model of Chinook density, and look at what happens to predicted Chinook densities as you vary that one factor, holding all other factors at their mean. And so you can look across the seasons, and this one's a little bit hard to read because there's so many graphics, but what I want to show you or highlight is that the line in these figures represents the Chinook salmon density as predicted by the model. The shading is your 95% confidence interval, and across some of these, we have different y-axes or different levels of density. And we'll zoom in as we go to the next slide to look at a couple of these in more detail. This top one is just that range of depth, right? When we talk about range of depth, we see that the highest densities on the y-axis are associated with a low range of depth on the x-axis. So that 0 to 50 is sort of a little bit of a break point across all seasons. And 50 centimeters is about half a meter. That's really not that much when we talk about range of depth. So don't think that, these are huge changes. It is something that showed up as significant, but that we're really talking about smaller changes and small depths probably overall. Percent wood cover kind of tells another story, that we're increasing densities with increasing wood cover, which makes sense. But that line's still going up past 60%. So to me, that's an indication that we probably need more wood in the Skagit. We did not see very many sites that were above 60%, if any, and most of our sites were in that, 25% or less range. And you'll see that a little later. But, understanding what these factors do across different seasons, singularly and together, can help us dig a little bit more out of the data set. And there's a lot more that can be done with this data. This is just sort of the first piece of work out of it. So those are kind of interesting. Moving on to the next slide. So then what does it mean? How do we boil it down so that people can actually use information and do something with it? And this is just an example using one of the factors. So looking at maximum water temperature, what we wanted to do was come up with some results that could be applied in a very pragmatic way. And so we created box plots of the data sets, and the left-hand box plot represents everything we saw. So every site is represented in the most left-hand box plot. And then the middle box plot shows sites that had STJ present. And then the right box plot, or grouping of data, is just looking at the best of the best. So within a season, what is the top 50% of the densities that we saw? So where were the most popular spots for these fish, and what were the habitat elements that were present in that top 50%? What we found is that even across seasons, we kind of got a singular message. We were able to sort of make this recommendation slide without squinting too badly at the combination of values that came out across seasons for that top 50%. And what we found were that depths are, you know, the most popular depths were fairly shallow. We're looking at 1/3 to 2/3 of a meter, which agrees pretty well with Beachy's edge habitat definition, and with other sort of, you know, most popular sites for a variety of salmonids across the literature. Mean velocity similarly fairly low. And we were looking at side channel and floodplain channels a lot, so this is not unexpected data, but this less than 1/3 of a meter per second, and that's in the range of what other folks have found as well for juvenile rearing. The mean D50 between 3 and 36 millimeters. So you can tell we're not talking about boulders here. We're talking about small substrate, and that matches up with lower velocities and, you know, sort of quiet water. The distance to main stem was one that we found across seasons and found that to be kind of interesting. The, you know, 119, 120 meters, that's about 400 feet-ish. So thinking about when you're looking at a site, you know, how far are these fish really going to move up into this side channel? And does it make a lot of sense for yearlings? Not, I mean, other fish may be completely more traveling, but from what we saw, does it make a lot of sense for yearlings to have 2 miles of space when they might only be moving up in that bottom part? Not saying we shouldn't build side channel habitat, because I'm absolutely in support of off channel and side channel habitat, and we'll talk about that a little bit more too. But just knowing, you know, where folks might be hanging out, and by folks I mean fish. And so then the temperatures, again, we talked about the max temperature in summer. You know, those popular areas were in that 15, 16, 14 range. 11 to 16 is that max range that we saw for the highest densities. And then wood cover, I would not recommend these as recommended wood cover percentages. It was just what was observed. And, you know, I would say that we may be below optimum levels in the Skagit with the wood cover, especially in some of these areas. But, you know, remembering that curve keep going up, that we could probably benefit by having a little bit more on that. And thinking about what could be next with this, you know, the model is available and could be applied at a larger scale. You know, you could use GIS and look at different features as they are now. You could look at features as they might be planned to be if you have, you know, predicted values for depths and velocities and things like that. You could use it for prioritization of channels or areas that might be targeted for restoration for different life history patterns, specifically yearling Chinook. It could be applied to other basins as well. And I'm hoping folks get the chance to do that in the near future. There's also potential to put out another habitat suitability curve and say, hey, here's another way to look at it. And maybe compare that to some of the Department of Ecology curves that are currently being used across many different areas. And that could be validated or tested, you know, with field observations or testing the two models against each other. Just trying to move the ball forward in terms of how we evaluate habitat quality, how we evaluate benefits with respect to restoration, planned restoration. You know, we can use models to help predict benefit at a much lower cost than going out there and, you know, counting everywhere if we don't have the funding to do that. So anyway, those are some just initial ideas, and moving on to the next slide. I just want to leave people with a question. This is one of the things that we observed when we were sampling, and spring of 2021 size distribution of all the stream type juvenile Chinook is on the left-hand side, and spring of 2022 is on the right-hand side. And recall that we had that big flood in November of 2021. And ostensibly, we may have some density dependence in our floodplain and off-channel, side channel habitat, meaning that there may not be enough of it for juvenile Chinook, specifically yearlings, maybe growth. And so what we saw, and we thought it was an error at first, but it's not an error. We saw these really large smolts. So over here on the right-hand side, you see that secondary bump that goes from 100 millimeters to up to 130, which is really, really large for a Chinook that you might be seeing in this system. And we didn't see that in spring of 2021 at all. So the theory might be that flood maybe had pushed out a lot of fish. And so those that were left had lots of space, They had lots of food, they had lots of resources, and so they were able to add biomass at a rate that we don't normally see. And so what this does for me or suggests is that there's a big need for rearing habitat for yearlings in the Skagit River and the Sauk Basin. And if we give it to them, they will take advantage of it and go crazy in terms of, growth. And as Erin said, growth translates into survival, and survival translates into productivity, which translates into bigger Chinook populations in the Skagit. So this to me is just a really interesting shift that the fish are telling us that, hey, if you give us a little bit more, we can really take advantage of it. And that's the end of this section. I wanted to thank all the folks that were involved in this study. Erin was a co-author, Mike Lemoyne, and other folks from Natural Systems Design were involved in writing this up, and then a large field crew of very hardy folks that were out there in lots of challenging conditions, snow and night and predators and things like that. And then the funding, majority from Seattle City Light, the non-flow committee funded most of the study. There was some small support from the Salmon Science grant out of the Puget Sound Partnership through their PSAM program. So analytical work was helped along with that. And then there's a picture of our cover page from the transactions article. So read that if you'd like. And that's all. I appreciate your time. Really appreciate the opportunity to present. And thanks, Erin, for your help as well on this work and leading the charge on many of the phases. And there's a question slide if you want to go to that, but that's where we're at.